Now, this may be a good juncture for us to introduce the idea of an active high and active low input, or an active high and active low output. Okay. Active high and low input / output. Okay, just to understand this, it's very interesting. So if you take that particular controller, control unit that we had, right? We take this control unit that we had. There is the SB, right? Seat belt, DR, right? Now, this is a Boolean output, right? But eventually this has to control an LED, right? This has to control an LED, and that LED has to glow based on this logic. So, if you look at this here, for example, I would want, right, this might be an LED, okay, and I could have such a condition, okay, as opposed to, for example, I will show you with SB that I could also construct this in an alternate manner. Okay, let me just draw that here. Okay. Okay, this is an LED. I am sure you people would have seen an LED, right? Something that is going to blink. Okay. So the difference between, between this DR and SB, right? So what we want here is essentially DR to basically be, to activate the LED only when DR goes low. So how does this LED work? It needs some current. If you allow some current to pass through it, right, it will emit some light. Okay, and this resistor is sort of just for a light sort of a current limiting resistor that is used. Okay, but the idea is very simple. So if SB happens to be 0, right, 0 volts, remember the logic 0 is, invariably it will be 0 volts, right, because of logic restoration and all that you saw in week 1 of this course. Suppose this were 0, then the LED would not glow because both ends of the LEDs are basically grounded. Whereas if this went to 1, right, if this went to logic high, then the one end of the LED is at close to VDD volts, right, 5 volts. The other end is close to ground, and therefore you will have a current through it and the LED will glow. On the other hand, if you look at this DR output, right, if DR is 0, right, so what I'll do is I'll indicate in red the state in which the LED will glow. Let's say the LED is red, right. On the other hand, when DR is 0, the other end is already connected to VDD for the LED, and therefore you will have a current, it will go, right. But when DR is VDD, you will have nothing basically driving this, right. And therefore, depending on the application that you are trying to sort of use, you might end up coming up with a different requirement for this particular truth table itself, right. So we call this an active high. Okay, in this case SB is active high, right. On the other hand, DR is active low. What it basically means is, when the activity is happening that we are interested in, it is going high, okay. Here when the activity is happening, it is going low. So by default, this dr will basically be 1. Okay, so you must yeah, so the dr will be 1 and then it will be 0. Right, this is how dr, and this is where the activity is, this is no activity. Right, on the other hand, the SB is going to look like this. Seat belt, no activity, and this is activity. Okay, so now if you consider this case, right, so what we already designed for SB is the active high case, right. When we wanted to indicate something, it had to go high. Now let us take the the second case and look at the active low implementation of the door indicator. Okay, so what is this? Again we have ignition D4, D3, D2, D1, D0, and we have the DR indicator. Okay, so this is something we must be careful about. If the ignition is low, it does not matter what this state is, right? Go back to this picture here, right? The inactivity state is logic 1, okay, and therefore the truth table also will this thing. So maybe I should call it yeah, this will be 1. Okay, then I have when the ignition is on, I'm going all the way, and then I'm going through the 32 combinations, right? Now when all the inputs, let's say all 5 doors are open, so here we have not changed the polarity of the inputs, by the way. D0 to D3 are still active high inputs, that is when the door is closed, we are saying it is going high. Okay, so all 5 doors are open, then we want the LED to glow. Okay, it will become 1 like this, 0 0 0 0 1, right? Of course we want the LED to glow, active low, remember. Finally, last combination, when all the doors are closed, you want the LED to be off, so you make that thing. So if you look at the last but one combination, let me write that 1 1 1 0, this will be 0. Okay, and for this you just write dot dot dot, right? So effectively your DR, right, maybe I'll call that AL, active low, right, is basically going to be summation 0 1 2 all the way to 15. Okay, then this is min term 16, this is min term, no, it's not 16, sorry, this is going to 31, this is min term 32, min term 62, right, 31, 32, they are all 0, sorry, so they will not appear here, and finally you're going to have min term 63, because this is M63. Yeah, right. So now what happens here? We are basically saying that we are taking this is the active high, DRAH. Okay, I'll just change this here, and yeah. So in some sense we are saying DRAH, right, happens to be a logical inversion of DRAL. Okay, and you know, if you try to do this Boolean simplification, you will get a certain expression which we can just show is all you have to do is take this AH implementation, right. So you have D4, D3, D0 ignition, and you pass it through a NAND gate, and basically you are going to get DRAL. Essentially this is what you have. Okay. So essentially when you therefore when you consider the active low implementation, it may be beneficial to directly design for, you know, considering the final application that you are looking at. Okay, like I told you, in this case the LED requires, you know, some LEDs you might have to connect to the supply, in which case the Boolean logic will have to drive it low. Okay, so you will have to appropriately design this particular logic accordingly. Okay, so that is you know, the overall idea of how we started with you know, a problem in the English language and translated that to the truth table and effectively into the gate level implementation of these things, right. So one other interesting point is that, you know, in case of the SB, right, the seat belt indicator, it was very straightforward. We needed only a 2-input NAND gate, right. But then now for this we need a 5-input NAND gate, and a 5-input NAND gate may not be available, right. So in that case we might have to find a way to implement NAND gates, you know, higher input NAND gates using fewer input NAND gates, right. So that is just a sort of a very practical and important consideration for this implementation here, which we need to be careful about. Okay. So one further variant, interesting variant I would say to this problem is, what if the inputs themselves were active low? Okay. So for example, S1 and S0, the seat belt indicators for each seat, right? What if that goes low when a seat belt is fastened? Right. So this again depends on how that sensor is actually made, right. So effectively it could be, you know, that when you connect the seat belt, there is some reason why this seat belt indicator itself would go low, right, indicating the activity, I mean the activity being the seat belt is fastened, and the indicator would go low at that time. Okay. So again in that case, the ignition S1, S0, right, compared to the door case, this is easier to handle because it's fewer variables. And I can now talk about the seat belt indicator, and we could now independently choose the seat belt indicator to be active high or active low, by the way. Okay, there is no reason to this thing. So we'll look at both cases, active high, right, seat belt active low. So again, ignition is 0, it does not matter what these two inputs are, ignition is 0, and therefore the active high case should be 0, active low case should be 1. Okay, ignition is high, right, that is car has been turned on, and now you are looking at 0 0, right? So 0 0 is the case when the seat belt is fastened. Okay, seat belt is fastened in the sense we are saying that these two, both driver and the uh, person beside in the front have fastened their seat belts, and therefore the seat belt indicator should not go high here if it is active high. Likewise, it should continue to be 1 in the active low case. Then you have 1 0 1 1 1 0 1 1 1. Okay, so again, in the other cases you want the seat belt indicator to go high, right? And therefore uh, this is sorry, uh, in the active low case, when both of them have put it on, yes, you basically want no activity there. Yes, right. And the other cases we are going to say this is 0 0 0 effectively, right? Essentially we are saying ignition is on, um, one of the two seat belts is not fastened, right? Um, yes, and therefore the seat belt indicator has to go on here, right? Therefore, in this case, the SB active high is going to be, so we have, this is a 3 variable Karnaugh map, so 8 combinations. So I can say sum of 5, 6, 7, and SB active low is going to be summation 0, 1, 2, 3, 4, right? So this is effectively what we have, and let's go ahead and look at the implementation of the SBAH. SBAH, okay. So, yeah, so 0, 1, 2, 3, no, 0, 1, 3, 2, 4, 5, 7, 6. So again this is S1 S0 ignition, right? IG bar, IG, S1 S0, S1 bar, S0, S1 S0, S0 bar. Okay. So what we have here for SBAH is we have 5, 6 and 7. Okay, and therefore this I can group like this, right? And SBAH, let's see, SBAH will be equal to IG into S0, okay, uh, plus IG into S1, okay. This is IG into S0 plus S1. So if you look at this implementation, when the input is active low, it is going to have the following structure, right? I'll draw the structure here. S1 S0, it's an OR gate, okay, S0 or S1, and then I am going to AND with this. So this is my okay, I don't have space here, so I'll have to move it. So this is my ignition, SB AH, right? And what did we have in the earlier case? Remember, that was not an AND gate. It's not an AND gate became an OR gate. It is a NAND gate that has become an OR gate here. Okay. So when you go from active high to active low things, your intuition might tell you that, oh, the OR gate will just become an AND gate. No, the OR gate will become a NAND gate, or the NOR gate will become an AND gate effectively. So that's what will happen. And this AND gate here does not change, because again the IG is sort of a gating signal, whether it is the ignition is on or not. So you basically just that logic, that AND gate logic is not going to change one bit, whether this is active high or active low. Now likewise, what happens if we had the opposite case, right? The active low case, I'll just write that in green right here in the same truth table. Okay. So basically, yeah, so this is very interesting. If I had active low inputs and the output was supposed to be active low, right? So I'm saying this one is going to be in green, SBAL, and this was in red. Okay. Now the green case is the following. SBAL, right, is IG bar, because I'm going to go through this guy. Okay, IG bar, and then of course I'm going to plus IG does not matter, it is S1 bar, S0 bar, right? So what does this simplify to for us? This can be simplified as IG into S1 into S0. So this is actually the best implementation is not obvious. So one way to implement this is to simply put the NOR here, S1 S0, right? And then we are looking at, yeah, so this is not so obvious. So you invert, yeah, so then you invert IG, okay, and you put an OR gate. Okay, this is your SBAL. Effectively, the implementation therefore can change quite significantly because of this active high and active low notion for inputs and outputs. So with that, we will wind up this discussion on Karnaugh maps and Boolean simplification and move on to the actual implementation of these circuits using practically available gates in the coming weeks. Thank you.